with the delta method. So today, we'll wrap up on the delta method. A little bit of a wrap up. Let's do an example from the book. So I think that's what we all like to see, maybe before proofs or something like that. So we'll switch it up what the style is, maybe examples forward, proofs later, and sometimes proofs forward and then examples. So I think the examples forward is, I like that. So personally, show me some examples of what you're doing and then tell me why it all works. But somehow in academia, we're like really inclined to go the other way. Does anybody have any idea why we do that? I don't know. So to confuse you, maybe it's purposeful. So I'm not sure. So I've never gotten a good answer to that either. Okay, here's an example. So let's say I've got xi's. They're coming from a Bernoulli distribution with parameter p. So that's just a coin flipping model. I'm just doing IID coin flips. So flipping coins, seeing whether or not it lands heads or tails. But instead of talking about heads and tails, I'll just immediately encode this as a 1 or a 0. So this is going to be an element of 1 or 0. And if somebody gave it to you in terms of heads or tails, you might say this is an indicator function that the coin landed heads. So that's an indicator. So the question is that 1 or a 0? So usually we define this is a 1 or a 0. This would be if the argument is equal to h, and this is otherwise. I could say tails, but there's only two things going on. So we'll be using that notation fairly regularly. Okay, so let me just write something down just as a prelude to what we're going to be studying when we're dealing with sufficient statistics. So somebody tell me real quickly, how do I write down this distribution, f of xi given p? So this is the sampling distribution. You might be thinking, don't use that little f thing, use something that makes a little bit more sense. This is your probability function. So oftentimes I just write little f. I do it all the time. So but we'll be a little bit more polite today. So probability. How can I write this down as an equation? I could write it down like this. Probability of this is going to be p if xi is equal to a 1. And this is going to be 1 minus p if xi is equal to a 0. I could write otherwise right there. So that's one way to write it down, but that's not a nice equation. That's hard to put into your computer. So what's a cleaner way to write that down?
P power xi and 1 minus p power 1 minus xi.
Yeah, exactly. Just kind of use this indicator notation to turn these switches on and off, but I've already got this encoded in terms of indicators. So this would be p to the xi times 1 minus p to the 1 minus xi. So I should probably be a little bit more polite and tell you that these are probabilities. So it wouldn't be a very interesting coin if p was 0 or 1. So that would be the trick coin. Okay. So that's how we write that down right there. Let's say I have a sequence of these things. So I have n of them. What's the joint distribution? F of cap x given p where cap x is x1 to xn. What do I do? But you could. But this is, a binomial concerns the sum of the xi's. You're 2 thoughts ahead, but you're on the right track. We could use that. So, and we get the same inferences, but it's not exactly the question. This is an n-dimensional thing. So it's a vector of everything. So how do I come up with that joint sampling probability? Take the product, it's IID. So I goes from 1 to n, p to the xi's, 1 minus p to 1 minus xi. So piece of cake. And if you coded this up on your computer, you might struggle a little bit if p was small or big. So, and n was large, and you're producting a bunch of smaller big things together. Your computer doesn't like that very much, and eventually it'll get around here. So you probably wouldn't want to encode that. Also, taking sums are more numerically stable than taking products. So you would probably rewrite this as p to the sum of the xi. I goes from 1 to n, 1 minus p to the n minus sum of the xi's. So, same thing. So, and so that's the joint sampling distribution. It's written down like this. And you'll notice something, that the information about this distribution I could write down in terms of all of the xi's. The sequence of 1s and 0s has all the information about this function. But you'll also notice that some of the xi's is the function the data is coming through that relates to whatever that function is. So if I were thinking about a likelihood function, a function over p with some of the xi's fixed, this is something that I could just pre-compute in advance if I were writing some code and just have that some of the xi's fixed. And I could even speed up my code quite a lot, you know, by not repeating that product every single time I evaluate things. So that's useful to do. Josiah mentioned the binomial distribution. So note the binomial dist is some of the xi's. It concerns this test statistic, and this is binomially distributed. The parameters n and p. And so what does this look like? Probability, sum of the xi's. I goes from 1 to n, given p. This is n, choose sum of the xi's. Times p to the sum of the xi's, 1 minus p to the n minus sum of the xi's. And they look eerily similar. So you'll notice the only thing that's different is the normalization factor. So this is accounting for all of the different combinations of everything. And if you were to normalize this, you'd have to enumerate over all the sequences of 1s and 0s. And so you'd be doing how many enumerations of all those 1s and 0s with a fixed number of that. It would correspond to that binomial coefficient. So the interesting thing to notice is if I were to plot the likelihood function of this, it has exactly the same shape as that. So the shapes of these functions are the same. And this is just raised up and down. It's actually up, since that number is bigger. That's a big number. That's some big number. So it's raising that function up, but it has the same likelihood function. I can multiply a likelihood by any positive number, and it's still the same function. So likelihoods are self-relative. So if I said the likelihood of a point is 0.7, it means absolutely nothing. If I gave you the likelihood of another point, then I could check in a ratio sense how much more likely that point was. So this is what we'll talk about when we get into sufficient statistics. Let's consider a slightly different question. and say, instead of trying to estimate P itself, I should ask a question. What's a good estimator? For P. And I don't mean this to be a trick question. The mean. So probably a mean. And it's not just a coincidence that a function that has something entirely to do with the mean is appearing in here. So it's part of the sufficient statistic. All language that will define next time. So the mean. So P hat, it's not quite P. So P is approximately that, whatever that means. How close is it? Probably has something to do with what n is. But this is just going to be the mean, x bar, n, sum of the xi's, 1 over n. So lots of reasons why we might like this statistic. You could verify it's unbiased. So expectation of this thing, P hat is equal to P, you can verify that. So the expectation of the xi's themselves is P. It's not hard to verify. What's the variance? Again, another Stat 101-esque question. Everybody knows, right? Go ahead right there.
P times 1 minus P over n.
P times 1 minus P over n. And if you were to derive that, how would you do that?
You could use an ungenerating function, or you could find the expected value of the x squared, use that, and you're just in the definition of variance, and then divide by n because it's mean.
Okay, I think I got the second part. So you would look at the first two moments to calculate the variance. Let's just do that real quick. Probably an MGF would be a bit of extra work, but that might be nice if you're trying to prove something. So just note that the variance of the xi's themselves is just the expectation of the xi's squared minus the expectation of the xi all squared. So what's the expectation of the xi's? It couldn't be a simpler thing to work out. I'll just use the definition. So this is just 1 times P plus 0 times 1 minus P. So if I just expanded the expectation, there's only 2 elements in the set. I use the basic definition of expectation, that's P. If I wanted the second moment, this is just going to be 1 squared times P plus 0 squared times 1 minus P. So definition of the second moment. And so that's pretty easy to work through. So that's P as well, right there. And so if I apply everything to this formula, this is going to be P minus P squared, right there, which is P times 1 minus P, which is this part. And then if I apply the average to it, I need to divide by the n. So you can pull the sum out of the expectation in the average, and you have the n squared coming out twice. The sum sums up n times, and you get a cancellation of one of the n's, and you're left with this. So all in just a Stat 101 review. So check. We'll need that for the delta method. So I probably should have probed you for this, but this is normally distributed. Or at least it's asymptotically normally distributed. That's the CLT. And so I like that. So now I know properties about how this thing is expected to vary. So at least if n is big. It's not my favorite thing in the world to apply CLT to this. So if I were trying to estimate P, what could go wrong if I applied CLT to this and n was 22? Something like that. What's the problem with the CLT in this analysis? CLT, normal distributions go between negative infinity and infinity. P is constrained between 0 and 1, so you could come up with some probabilistic inferences that don't make any sense. And so that's the problem with just applying an asymptotic argument directly and it's not big enough. And so it doesn't necessarily adhere to the bounds of the problem. So that's not baked into everything. So if somebody says, what do you think P is? And I build a confidence interval out of the normal distribution, doing the pivoting sort of thing that we typically do. I might say, oh, I think P is between -2 and 4. So, and somebody goes, I agree. It's perfectly useless. So, anyway, regardless, if n is big, maybe the CLT is helpful for us. So let's consider a transformation. So consider the transform. P over 1 minus P. This is called the odds. If we wanted to make this problem more difficult and make the delta method even clunkier than it already is, I could take a log. People do that all the time, log odds. And so that could really muck around with things. I'll tell you what's happening that's really bad about this is if all of a sudden P is close to 1, I have a very good chance of dividing by 0 in this estimate. And so that's not good. So giving an estimate that's like infinity, that's not an actual answer. That's not a number. That's a concept. So not helpful. So anyway, that's what's going to be kind of heinous about this problem. So I won't make it more difficult than it already is computationally. I think this is good enough for us. So when I do have you simulate this, you're going to have nans and imps being thrown around. I love that kind of stuff because it makes you think about something. So, and you need to quantify how often the method actually works in the first place. So consider this transform right here. I'll call this GP. So if I wanted to apply the delta method, what I need to do is compute, I'll say, these are the first 2 steps. I'll come up with expectation of P hat over 1 minus P hat. If I were to estimate this right here, and I can come up with some property, and this is basically what the delta method has you do for the mean of that distribution. It's going to be roughly P over 1 minus P. It's not exactly that thing. So how far off is it will determine how well the delta method is working. And the variance could be a difficult calculation to work through. But instead, we'll do the approximation that the delta method suggests. So G prime P squared times the variance. And you plug in the actual test statistic that you're writing down right here. The way the book would have written this down in terms of its limiting theory, when it gave you the theorem of the delta method, is this would have been the variance of the xi's over here. They would have had the n pulled over on the left-hand side so that I could take a limit and have something make sense. So when you actually apply this in practice, you take your test statistic that you're playing around with and you throw it in there. So we already know what that is. That's P times 1 minus P divided by n. And now we just have to take a derivative, and we have to remember to square that derivative. This is the part that I would misplace. Not a hard derivative. Does anybody remember the quotient rule? Good for you. I do not. So I'm sure I could. There's something squared on the bottom. There's whatever. So take the problem. So G I'll say G prime P is equal to the derivative of P times 1 minus P inverse. So change your quotient rule, always into the product rule, and you only have to remember one of them. So derivative of the first thing, I can do that pretty easily. So I got the first thing, I got the second thing. So derivative of the first thing is 1 times the second thing, 1 minus P inverse. So be a little bit careful with this symbol. So I'll take the derivative of the second thing. Let me first multiply by the first thing. That's this. Derivative of the second thing minus 1 comes down. 1 minus P, and then I apply the chain rule. Derivative of 1 minus P, and it changes that to a plus. Minus 2. I didn't finish taking my derivative. Okay. So 1 over 1 minus P, I can never do this until I put it back into fraction form. 1 minus P squared. Combine, make the denominators look the same. So I can do that. Exactly the same thing, didn't change anything. And so minus P plus a P right there. This is going to be P, this is going to be 1 over 1 minus P squared. So that's our derivative. And so this is going to be 1 over 1 minus P squared, squared again, so that's to the 4th power. So there's a cancellation with one of those. And so this looks like P over 1 minus P to the cubed. And if you don't see n's appear in your variances, you'll always know you've made a mistake. That's at least a rough rule of thumb. So make sure that n still appears there. So that's my approximate variance. And now we can apply the delta method. So the delta method says this, at least in practice. The theorem is a little bit different the way that it's expressed. So I should say the delta method implies, maybe this is close to a useful statement. So P hat over 1 minus P hat is going to be about, this is an approximate statement, it's an asymptotic statement, this is normally distributed, centered at P over 1 minus P, and then I have whatever we computed for variance, cubed divided by n. So one of the things I'll have you do is I'll have you simulate this and demonstrate how good this is. You could check this. So I could just keep sampling out of Bernoulli n times, compute my test statistic, do it again over and over again, make a histogram of that test statistic and see how it varies. And I could overlay this normal distribution and see if this is approximately true statement. And I think for reasonably sized n, even relatively small n, like 10, yeah, this actually looks pretty good. So you probably want to crank up n big enough so that you don't have your divide by 0 errors. So probably when p's not close to 1, this looks really good, or if n is really big. So all you need is one failure in all of that, and you won't get a divide by 0 there. So I would say for n50, this looks really good. And I'll have you demonstrate that. This is not an inferential statement. So this is just a probabilistic statement. It says something about this thing that I'm computing has that distribution. And so if I were doing inference, I might be inclined to go and graph this thing right here and just say, if you want to study this, it's good enough to just study that distribution. But this is impossible for us to do in an inferential sense because you don't know P. So if you knew P, you wouldn't be doing stats in the first place. So instead of working with this distribution, what you might do, again, we'll get into the precise definition of this. Did Chris show you what this was in his class? At least define what a pivot was. Okay, cool. So I'm going to just say very hand wavy. All I do is I take my p's and I substitute an estimator for them. So there is a more technical definition than doing that. So, but in an engineering sense, I'll just estimate everything in here. I've got an estimator for p. P, it's p hat. And I'll just plug that stuff in. So p hat, 1 minus p hat. There's a cube in there. And so I might study that distribution. So if I wanted to build a confidence interval or do something and make a probabilistic statement about something, I've got to have the parameters defined before I can actually do the calculation. And so the question is how well does this characterize everything? So is the variability a good expression of variability of that test statistic to be useful to do inference? Okay. Any questions? Delta method is right. I'll have you practice this in the future. I'll give you a supplementary exercise, and it basically mimics what they do in the first part of chapter 10. We'll come back to this later. Let's think about this problem totally differently. Let's think about what a Bayesian might do. And the only reason I do all this is just so that we can compare everything. So we can think about what are the relative advantages to different branches of statistics. So there's trade-offs in everything. So, Bayes, let's study the exact same problem. So, xi's are coming from a Bernoulli. Everything's IID. I goes from 1 to n. So exact same problem. Instead of trying to infer p over 1 minus p, I'll say let's start with inferring p and then just transform it. So if I've got the distribution for p, then I can figure out what the distribution of p over 1 minus p is, which is 1 to 1 transforms. So somebody tell me real quickly, what do all Bayesians do? All Bayesians at least agree on this part. Yeah, I would say that. So they do inference off of the posterior. So all Bayesians do that. So they compute something like this. P given all of your data. Same notation as before. It's called our posterior distribution. So as soon as I see that somebody has the data fixed and they're characterizing a distribution on the unknown parameters, I don't care what they call themselves, I'll immediately think, oh, they're Bayesian. So no big deal. Then I might ask some questions about, things about their prior or what the properties in their posterior are. So how do we get this thing? We've talked about this a little bit. So this is always likelihood times prior. And then I normalize everything. Just so this is an actual distribution, then I know what's big and I know what's small. So I'm going to integrate over the whole universe of p. That's I'm going to integrate between 0 and 1. And I kind of like it. So they'll give you a probabilistic inference on the parameter itself, where the other stuff we were doing, we were characterizing distributions on the test statistic, which is different. So they're backwards from each other. So Bayesians think in the correct direction, and other people think in the backwards direction, unless you're turned the other way. So, and then you'll think the Bayesians are all backwards. So it's up to you. Okay, we need to talk about the prior. So let me give you a different definition, conjugate priors. So a conjugate prior has the property that if, and I'll just write down, this is proportional to just likelihood times the prior. That's where all the action is. That's where the shape of the distribution is. That's the only stuff that contains a P in there. So that's what we're doing inference on. So that's all I really need to know. If I knew this thing, then I can normalize it. So this is the kernel of the distribution, right there. The kernel of the posterior distribution. So conjugate priors have the property that if this, the prior and the posterior live in the same distributional family, the prior is said to be conjugate. So if you've heard that word before in other disciplines, I mean something different. So that word is used all over the place, and very often it means something different. So I don't mean anything about imaginary numbers. So it's nothing to do with that. So conjugate priors have the property that if the prior lives in some distributional family, I don't mean anything as broad as the exponential family, I mean actual distributions. So, like I mean something like a binomial distribution or a Poisson distribution. So, a constricted family. So, the exponential family, I'd say, is families over families. It's your big family. It's not your immediate family. So, if this and the posterior lives in that exact same family, these are the same, then the prior is said to be conjugate. And there's no other way to do this other than to just know things about distributions and to be able to recognize everything. So what I like to do is I like to write down the likelihood function and stare at it and say, what can I multiply by that preserves that form and it still has that same analytical algebraic form. So let's just write that down. So likely the posterior distribution is going to be proportional to the likelihood. We've already written that down. Sum of the xi's, 1 minus p to the n minus sum of the xi's. So what do I do to come up with my likelihood function? I write down the sampling distribution, and I do that conditional flip in my mind. What's the argument of this function? The likelihood is a function over the parameters. And this thing is fixed, times pi p. So I have to think about what distributional class do I know about that I can multiply by, and it's, once I slide it through the likelihood, it has that same exact form. And I think we've alluded to this already. So what's the distribution? It's beta distribution. So the beta, and this has 2 parameters in there, is conjugate. So that means, I'll just write down the likelihood, p sum of the xi's, 1 minus p, n minus sum of the xi's. And I know what a beta looks like. We've written it down before. So you can check your notes. Let's forget about the normalizing constant. It's called a beta function. It's all we can write down is something in terms of an integral anyway. And so I can give it some nice notation and call it a function and say I could use a computer to calculate it. I've written down the proportionality sign in the first place, so I'm tossing all my constants as I go. So we're just going to forget about it. So the beta looks like this. P to the alpha minus 1, 1 minus p to the beta minus 1. And I will mention these are supposed to be positive. So those are the bounds of support for beta. So betas are distributions that live between 0 and 1, and they're very typical for modeling probabilities. And so this thing right here, over on the left-hand side, is just p to the sum of the xi's plus alpha. Let me give myself a little bit more room. This is p to the sum of the xi's plus alpha minus 1. That's that. I never absorb that into anything because I need that minus 1 to recognize what the updated parameter is. 1 minus p n minus sum of the xi's plus beta minus 1. And so this thing is a beta. And it has these two parameters. I'm going to call that alpha tilde, my updated parameter, and this beta tilde has something to do with the data. So this is a beta alpha tilde, beta tilde. So the prior is a beta, the posterior is a beta, so it's conjugate. And why we like that is it means if I know properties about my prior distribution, then I know all my properties about my posterior distribution. And so when we're doing if we're following the lingo, a priori, I have belief that P is distributed beta with these two parameters, alpha and beta. And once I update a priori after seeing my data, then I update my beta distribution by using the data. And that's where that lingo comes from. I don't love it, so because it kind of implies that we need to know something a priori. So maybe I just need to know properties of how this posterior is acting. Let me just ask real quickly, what would good choices of alpha and beta be? If we were to be Bayesians and actually do analysis off of that distribution, I have to make a choice. And this is the part where everybody kind of recoils. But people make choices all the time. So I'm not quite sure I understand it. If you watched Colloquium yesterday, she made a lot of choices. So, what do you think? Hard to say, right? I wish I knew more about betas. So what I want to do next time is come back and do a simulation study where we actually study the beta distribution. So just one more minute. So I wrote a piece of code that simulates this for us. We'll come back next time and we'll flip the coin some number of times. I picked some number of parameters. So my code is going to have a number of input arguments. I'm going to input in true P so that I can simulate the data in the first place. And that's the only place that I'll use P is in simulating the data. And then in my plot, I'll show you where true P is so that we can compare our distributional inference, our Bayesian inference to that. I also have parameters for alpha and beta. Those are my hyperparameters. That's what most people will call that. So the parameters that underline your prior are called hyperparameters. It's a name. Sounds kind of cool. It's almost unbelievable that a statistician would have come up with that. Because it sounds good. Iterations is just the number of times I'm going to flip the coin. So we'll come back next time, but what I'm going to spend some time doing is showing you how flexible beta distributions are. So I'm going to pick true P to be 0.7. I'll pick my hyperparameters to be 1 and 1. Jared, how do you like those?
They're okay. It's probably going to bias it towards
Maybe
1.5.
What's a beta 1, 1?
Uniform.
It's uniform. So it's a uniform distribution. So that might feel pretty good, you know, but it doesn't actually bias things towards half. So the expectation of a beta is alpha over alpha plus beta. And so it's actually cutting the expectation at 0.5. So it's biasing it towards the middle. So true P is 0.7. So it's adding a little bit of bias to things, but it's the uniform thing. It's not exactly the choice I would normally make, but it's the choice that most people will jump at. And I'll tell you a little bit about other choices. But we can run this thing. Do that again. We'll slow that down next time. True P is here, and as you saw that curve move, that was my 10 different coin flips. So I can recomputed that data after every time I saw the coin flipping. So sometimes you'll see people talk about Bayes as a sequential updating scheme. It's a very natural one for doing that you can just sequentially update your posterior at every step. This is the beta distribution right here, and that's the truth. And the question is that quantifying that very well? So, and what are different choices of alpha and beta, how does it impact that? So we'll come back and we'll slow that down next time. Study beta distributions, look a little bit more at what a Bayesian does, and then wrap up by discussing the transformation. Does anybody know what happens if you take a beta and you transform it to P over 1 minus P? It's called a beta prime distribution. So I didn't know that before I worked through this example. And I was like, this has to have a name because you can work it out in closed form. And it turns out it does have a name. And so we can look at that distribution next time as well. That's it for now, you guys. So have a great weekend.